Hi guys, my name is Nicolás and I'm going to present to you a parallel implementation of a methodology to fuse multiple land cover products in space and time. The motivation for this project resides in that the land cover is a very important variable for many environmental processes such as evapotranspiration, infiltration, albedo, and reflection. Therefore, in recent years, remote sensing technologies have focused on the development of land cover products. So what's a land cover product? This is an example of a land cover product. It is basically a picture of the land surface where each pixel has a specific land cover category such as urban, forest, or water. This timeline presents some land cover products available in the Rocky Mountain region. As you can see, the products that are very frequent in time don't have a high spatial resolution, while the products that have a high spatial resolution are not very frequent in time. However, many environmental studies require land cover products that have a high spatial and temporal resolution. Furthermore, even if the available land cover products fit your required resolution, the selection of the most appropriate one is not trivial, because first, their accuracy statistics are usually not comparable, and second, they usually present noticeable disagreements, as shown in this example. For the Rocky Mountain region in the year 2001, there are 4 land cover products, and even after reconciling their classes into 9 common categories, they still present noticeable disagreements. Consequently, we developed the spatial-temporal categorical map fusion methodology, SCAMF, which allows you to take multiple land cover products and combine them into a single product with your required spatial and temporal resolution. The core of this methodology resides in this equation. So let's try to understand this equation in simple English. First, the underlying green part of the equation represents the probability of a specific land cover class C to occur in a pixel of a grid where we are predicting. How do we calculate that? First, we go through all the land cover products. Then, within each product, we go through all the pixels that are in a spatial and temporal neighborhood of the pixel that we are predicting for. From those pixels, we only take into account the one that have the same land cover category as the one that we are calculating the probability for. And finally, we weigh those pixels depending on their spatial and temporal proximity. We scale the whole thing with the underlying dark blue part such that the probability is between 0 and 1 and the sum of all the probabilities adds up to 1. The calculation of lambda sub c involves many more steps and statistics that go beyond the scope of this presentation. However, if you have any questions, please leave them in the comment section and I'll do my best to answer them. The application of SCAMF in a large region such as the Rocky Mountains at high resolution is computationally expensive because of the number of pixels. Therefore, we developed our methodology focusing on 4 small domains within the Rocky Mountain region. I am going to focus on domain 1 to highlight some important features of SCAMF. First, it has a probabilistic character. That means that with the probability maps for each land cover class, which are the grayscale maps, you can estimate the certainty of your prediction, which is the red and green scale map. Also, the model parameters are optimized such that Q of theta, which represents the agreement of the predicted map with respect to all the other land cover products, is maximized. To apply the methodology in the whole Rocky Mountain region, we used parallel computing. Initially, we had a manager processor that divided the pixels among multiple worker processors. Each worker did the computation and sent the results back to the manager, and the manager wrote the results into the probability and prediction maps or files. For this, we use the GDAL library, which allows us to deal with geospatial data. However, this approximation was not very efficient because the manager had to deal with too much information, while the workers could have written the results directly into the probability and prediction maps. Consequently, we changed our implementation so that we didn't have to use the GDAL library to write the results into the files, and this allowed us to use MPI IO, which in turn allowed the workers to write the results simultaneously into the multiple prediction and probability files. This is an example of the parallel implementation for the Rocky Mountain region in the year 2001 at a spatial resolution of 50 meters, which represents 176 million pixels. We ran our simulations in the supercomputer from Colorado School of Mines, MC2. It was a full machine simulation, which represents 512 nodes, and we used 32 tasks per node. This resulted in 16,000 tasks. and because we had 10 files open at the same time, we had 163,000 simultaneous file descriptors. The code presented almost linear speedup with the parallel implementation. Future work involves some small statistical improvements, such as accounting for multivariate relationships among the land cover classes. I would also like to mention that SCANF can be applied to a single land cover product or to any categorical map to down or upscale their temporal and or spatial resolution. Thank you so much for watching, and if you guys have any questions or comments, please feel free to leave them in the comment section, and I'll do my best to reply to them as quickly as I can.